This is what StarWind wanted to demonstrate. However, we have an opportunity here because we have a group of folks who are actively working on an NVMe implementation, and we've got a group of folks around the table who are very excited about this technology. So what I would like to do is to have us spend a little bit of time talking NVMe as a group with StarWind, with ourselves, and let's talk about this tech a little bit, because I had the other day I had a company come to me and they said, "What's interesting in storage right now? What is the thing in storage?" Well, obviously, right? So they're like, that was my response too. I was like, well, duh, NVMe over fabrics. I mean, that's the thing that people are talking about right now.
So what sort of performance numbers have you gotten out of non-Optane NVMe SSDs? Because, I mean, not everybody's going to spend the money for the Optane solutions. I mean, not saying Intel's coming up and all that stuff, but...
So based on sales so far, nobody's buying Optane. We deliberately chose Optane to show that the code is there to push the Optane to the maximum. This means that if we take datasheet IOPS values from any other SSD available on the market, we'll be able to hit those numbers. And I think on this hardware Taras mentioned to me earlier, we managed to max out the initiator at 1.9 million IOPS. So we have to change the hardware now so the initiator can get more performance out of the target. In this case,
that's the CentOS initiator, right?
It was for devices striped yet, and the problem is that initiator is not powerful enough to generate the load, right? So on this particular hardware, I could squeeze it up to almost 2 million. So it was 1.9 out of 4 Optanes. But I could do an how would you call it? So like bake eggs on the CPUs, on the host. So
So the server scales with number of Optane SSDs. So it goes from 550,000 to almost 2 million?
Yeah, so it's almost linear. So it's 2 cores per NVMe, and it adds in 550 with NVMe.
And it would be 2 cores would be assigned to each NVMe SSD kind of numbers, right? Yeah.
And this goes back to Horst's question about using TCP. I mean, it would be possible if we would be constructing just storage-only nodes. So like there's a CPU and it has nothing to do. So let it just move the data. However, we are also in the hyperconverged business, and we don't really want to take all the the CPU horsepower and just throw it on data processing. We also want some of the CPU cores to do some kind of the just run some commodity VMs from the customer. This is what they are actually buying our hardware for. And while it would be possible to use DPDK to do a blazingly fast processing, for data without using of zero-DMA technology, it will just burn all the CPUs on that, and that will be pretty much it. And that's why there is not really much interest in doing that. And also, we don't see future in TCP stuff at this point.
Customer is going to want 2 million IOPS on 4 devices, and an SMB customer or a robo customer. I mean, it's a high-end storage.
No, it's so in that second use case, Vlad mentioned, it's SMBs as VMware and Microsoft classify them. So
exactly correct. So just getting a little bit deeper into that case. It means there is a fundamental issue with Microsoft and VMware licensing. So every time you are running just out of the capacity, you have to. Their idea is okay. So no problem. Just bring in another node, which is fine. But you have to license not only like vSAN and or storage spaces direct. You need a data center edition on this node, but you have to relicense all the software running on this cluster, and it can be a comparably simple and easy database, which just runs customer transactions in the real time, or selling tickets and so on. So it might be not that much of its typical robo location, and it have to run online all the time. It can't be moved to public cloud, and it have to provide reasonably high capacity. At the same time, just because there are quite many of these locations, like countrywide or worldwide, it doesn't really make sense to mess up with the different licensing. Also, going back with all these million IOPS, what we had found, if customer has a comparably small markup on performance, like if we are doing, using Supermicro hardware, and you can get probably like 10 or 20, maximum 20% up compared to SATA and SAS SSDs. And if you can go all NVMe, customer just check the box and I want it. Why you want it? Like, I don't care. I can do it, so I'll go for it. I'll figure it out later.
We learned from people buying all-flash arrays that if faster fits the budget, they're going to buy faster. It doesn't matter whether they need faster.
Yep. Exactly.
And if you need twice as fast, you pick the product that's 10 times as fast, because you don't trust the guy who told you it was 10 times as fast anyway. If it says it's 10 times as fast, it's probably 2 times as fast, which is what I need.
And it also opens another very good use case. It may be funny, but it might sound a little bit weird. But for example, using all flash for backup, it sounds like crazy. Backup should be something ice cold data, should be spinning disk or tape or whatever. Unfortunately, it's not the case. So we got the customers right now who are coming and asking, can you guys build as a backup appliance which will be all flash? Because right now we're using Pure for it and it's just too damn expensive for what it does. So it's like what? Why you want to do that? Say, hey, you know what? We're in trading business. And we just need, blazingly fast backups and very fast restores. And nothing except flash can do that. So it is exactly bringing a completely new opportunity to this one. And some initial set, like
blazingly fast backup device, secondary storage device. Is that?
Yes.
And this is financial trading shops need that because they can't be down.
Not only that.
We all think of backup as a sequential data stream, but if you look at a change block tracking backup out of VMware via Veeam, that is not a sequential data stream when it hits the backup target.
High frequency traders, are they using virtual storage?
No, I'm not saying. Yeah. I'm saying that it's not just high frequency traders. If I've got 2,000 VMs that I'm backing up with Veeam, and those data streams are much more random than what we're thinking of, because you and I, when we think of tape, then I do need to have 10 or 50,000 random IOPS. And if I need 50,000 random IOPS, all flash is the easiest way to do it.
And
50,000 random
Yeah, but then
you
need also a lot of capacity if you have hundreds of virtual machines. So.
Yeah, but
50,000 IOPS, not even breaking a sweat with this machine. I mean, it's hardly even, it's noise.
Yeah, but we're not, I don't think Anton's saying
Optane.
Customers are asking for Optane as backup.
Still. Yep.
They're asking for
Fast.
SATA SSDs as backup.
And remember, what you just said was that customers order 10 times faster when all they need is 2 times faster because it fits their budget, right?
Right.
I mean, think about Ray. I mean, we're graybeards. I'm a virtual graybeard. Well, gray head. I don't know. But remember when people were like, "Are you kidding? You're going to store like secondary storage on a Symmetrix? Is that so expensive? Are you kidding?" I mean, remember? I mean, oh man, you're going to use a fiber channel SAN for backup data? Are you nuts? I mean, Flash is not exotic anymore. I mean, just regular old Flash. I mean, a lot of people are going all Flash. I'm not at all surprised to think that some people might want to do backup to Flash and even backup to NVMe.
Yeah,
Sure.
Actually, now the price is going down very, very quickly, and QLC will
I've
change
talked to a
the
couple
game.
of very large enterprises who we don't buy spinning disks for the data center at all anymore, period.
Whoa.
Nice.
And faster we go, we'll try to speed up the adoption and just get rid of the things like SATA or SAS SSDs, or like move spinning disk, which is not obviously going to die anytime soon, but put it in a niche like tape right now is, and just make NVMe a commodity, then faster everybody will be using it for very different cases. It will just open and pop up and new opportunities, and the price will go down even faster. And this is what we're trying to do really here. So what we created and what we showed today is basically a very fast teleport. So we're taking an NVMe card from one place and we are getting it to the another one. And thinking about as an ability to do a kind of the trick, and it will be used by us in many different products that we are building. And we'll be happy if somebody will come up with more ideas to do it. Because
Anton,
what's that? Yeah.
A lot of the bigger vendors are concerned a bit about the state of the NVMe over Fabric standards. And how do you talk about that? I mean, they're saying to some extent that they're not stabilized yet. They're still waiting for them to be stabilized before they implement that sort of thing. Do you consider the NVMe over Fabric standard stable at this point, or?
No, absolutely not. Nothing is stable, and this standard is not stable. So it's missing a lot of things like security. It's missing also manageability layer, and this is pretty much obvious. And the idea is, if we're going to wait for something to stabilize, we'll be waiting for years. That's why we see that some particular tasks can be solved with NVMe or Fabric's protocol as is right now. Like, is it complete? No. Is it is it okay right now to be usable? Absolutely yes. So we'll put it where it can fit right now. When we'll see that there is no much of the and some kind of the security should be added, we'll wait for for upcoming spec to be released where it is pinpointed right now.
And if I could add, I mean, the main problem with chasing standards is if you're doing hardware, right? For a software group, it's pretty easy to make modifications. And if you push off the risk on the hardware side to someone like like an Intel, they're better equipped to handle it. So I mean, it's unfortunate that it's rolling out this way, but for your guys' position, you're probably in an ideal situation to be able to adapt to it.
And the only way to know what it needs, what the standard needs, is to implement it. That's what I feel like.
You'd think so.
Eventually, NVMe is going to be the storage protocol.
Yeah, well, there's no.
But the only way to do that is to exercise it. And you have to say what happens if we put backup data over this, or what happens if we put this in a phone, or what happens if we put this in a box with a box.
There's no sense in holding the first NVMe over Fabrics product for when NVMe over Fabrics is good enough for a Fortune 500 company to run SAP on it.
Yep.
There are lots of use cases outside of enterprise mission critical.
Is it T11?
No, it's the NVMe org.
NVMe consortium.
NVMe over Fiber Channel.
Somebody make those T-shirts.
It is T11, but NVMe over Ethernet in all of its flavors is the NVMe working group.
Which is under what?
Its own thing. It's its own consortium.
Okay, so it's like the wireless. Okay.
Yeah, and so the 1.1 NVMe over Fabrics 1.1 is in the jot and tittle stage.
Okay.
And it's lacking a standard method for multipathing. So it's the version after that. But we've got it runs on RDMA, it runs on, and TCP's in 1.1. So it runs on iWarp, it runs on Rocky, it runs on TCP. It's interoperable, you can make it work. Some of the HA stuff isn't in there yet, some of the management stuff.
Are we having PlugFest going on anywhere?
Yeah, UNH.
Good, okay, all right.
In fact, there's a PlugFest week after next at UNH.
Okay.
So I had a question about, from the internet about the benchmarking you did. Did you have a play around with like 64K sequential writes, reads? Like, how did that look in terms of?
So as I told already, I've spent a while playing with the queue depth and the threads number to saturate the hardware at most. So just playing around minimum, maximum, and so on. For this particular Supermicro host, the 10 threads and 32 queue depth was the optimal value. The CPU load and the IOPS I could get. So the maximum IOPS I could get.
So on 4K random, but did
on
you
4K random,
4K
right, exactly.
Writes or? anything bigger or smaller?
We tested sequentials and so on, but the more block size you get, the less load you have. So obviously, because the bandwidth grows only, right? But the less IOPS you have, the less load you have. So the most at 64K and bigger, it's less interesting than, in sequentials. We don't talk about sequentials at all because on NVMe. So the 4K random write is like the best pattern to benchmark it because it's very complicated, obviously, and it saturates hardware at most. So we've been using this pattern for this.
And the thing you were trying to expose was how much the fabric affect relative to the local.
Yep. Exactly. Yep.
And so, but the one piece you were missing is the QDepth1 latency, because that's how much does the fabric add to one I/O.
Yeah, that's something I will try as soon as I get home.
Yes.
Just to summarize, so we'll definitely publish a quite deeper, deeper research. So doing like many different patterns and showing all these things and going back to overhead of the fabrics. If we'll push a little bit more of the load on the hosts, we had found out that it's funny, but it might be that running the test over the fabric is actually faster than running stuff in the loopback. So you've seen the numbers a little bit higher when doing this kind of the redirection, because it turns out that if we're burning the same CPUs on the same machine for both load and for NVMe driver and also for test one, it's actually getting slower than just doing a segregation and putting the target initiator on the different ones. So network, NVMe or the fabric can be faster than NVMe itself.
So you have like a software. You mentioned you have a software-defined storage. Is that something that would layer on top of your NVMe initiator and target? Is that how you'd see this working, or you think that's a waste of?
No, at this point, as we do not want to play, let's say, not very nice against VMware and Microsoft, so we push this one as a complementary solution, saying, hey, you guys build your own stuff into operating system. But you have a like fundamental issue, like you cannot, if the host is running out of the slots for flash and you need more of it, there is nothing except customer can do except do a very expensive forklift update. And we are giving a customer an ability to get NVMe from other servers that has the spare slots and have their workload running, doing different things, and we can teleport this flash into where it should be doing. Obviously, at some point we are going to do a little bit more and to do the our typical mix of erasure coding and replication, and do highly available NVMe over the fabric's target, and also make sure that somebody has an initiator. NVMe as the fabric's initiator, he can run his workload against this highly available target, but in the way we want this HA to be done. So that's it.
Yeah, this brings up another point that we were actually talking about this yesterday with some of the delegates. NVMe is such a different world in NVMe over fabrics that some of our assumptions get thrown out. We just heard that running NVMe over fabrics can be faster than running it over a loopback, just because you're going to different cores and different CPUs and so on. We were talking about yesterday that you have to ask yourself some fundamental questions about storage system design. Does it make sense to do compression in NVMe, or is that going to hurt performance? Does it make sense to do whereas before it would help performance, because if you're writing less data, you can use.
Yeah, when the CPU is way faster than the media, compression adds performance.
But are we past that point of the hill now where it slows things down?
We're certainly at the point where they're in the same neighborhood.
Yeah.
Where the CPU performance and media performance are close enough that we have to ask the question.
But the value of tweaking is always going to be at the bottleneck. So as the bottleneck moves around, the value of those tweakings will change.
Right, and sometimes you're willing to give up some of the performance you have in excess to save some money.
Oh yeah, or for consistency, or for for lots of things.
It'd be interesting to see where the knee of the latency curve is as you go from 10,000 IOPS to 550,000. Latency goes from 10 microseconds to 500 microseconds or something. But someplace it's not linear, right? It's got to be some sort of a curve there. And where is the latency jump above 50 microseconds, for instance? Is it 500,000 IOPS or is it 100,000 IOPS?
Closer to 500,000.
Closer to 500,000.
Yeah.
Showing that curve would be very interesting.
Yeah, so it's something when I prepared, I was looking at these curves, but then I realized it's like moving.
I mean, the 551,000 IOPS is great. It's a hero number, but showing the fact that you can do 500,000 IOPS with this device at 10 microsecond latency or 50 or whatever it is.
Yeah, so basically we could guarantee that 400,000, like 450 would be still in the range under 50 microseconds.
I'd show that. That's
I think that's a pretty impressive.
Yeah, I think for NVMe over fabrics, the magic number is somewhere between 100 and 200 microseconds.
I'd say under 100.
That how many IOPS you can do at 100 or 125 microseconds is what I care about more than how many IOPS you can do at a millisecond.
Well, and instead of just speculating on numbers, let's say why you would pick that number, right? You would pick 100 or 200 because that's the point where it's a real noticeable difference.
Because that's where it's substantially different from the all-flash array that's based on SCSI, where the magic number is 1 millisecond
or half a millisecond.
And so we want to say, if we're going now, I don't believe NVMe over fabrics is strictly about low latency. But if we're talking about that very fast low latency NVMe over fabrics piece, then it's got to be not 10% better than a pure running flash, but it's got to be, here's the number, because when I measure all flash arrays, I don't care how many IOPS you can do at 2 milliseconds.
Yeah.
You bought an all flash array because you want under 1 millisecond performance. And so how many IOPS you can do at 1 millisecond is the magic number, not how many IOPS can I do and then what's the latency.
There are fairly expensive all-flash solutions today that quote 100 microsecond latencies at millions or 4 million IOPS, but these things are hundreds of thousands of dollars solutions, right?
Right.
Here you've got effectively two things of software, a Mellanox switch, and it's doing 2 million IOPS with 4 devices. But what was not impressive was the half millisecond or 0.6 millisecond response time or latency. Had you said it was 450,000 IOPS per device at 100 microsecond latency, and that's it's still close to 2 million IOPS at 100 microsecond latency. This is with 2 of these guys, which might cost, I don't know what the Optane devices cost, but the software is relatively inexpensive, and the Supermicro is relatively inexpensive, and the Mellanox is relatively inexpensive.
Software, maybe they are charging.
You can have a $4 million IOPS system with 8 devices or less.
So unfortunately, at this point, it's all very nice and exciting, but it's a little bit, we are going to give all this performance and low latency to software-defined storage stack, which is sitting above us, and they will just screw everything. So you won't see it in the real world, unfortunately. Because all these guys that were designed, mostly for spinning disk and for flash, which is like 10 times or like 20 times faster than just spinning disk. So they have no idea what to do with this performance. This means that we have to take take the job completely on us and build the whole storage stack from ground up. So just from very basic, from hardware level, then we are at the data mover level, and we then will build the initiator, and then make sure that we can pull all this, build the erasure coded pool of the NVMe devices, and show this latency not just for individual ones, but for a complete, distributed pool. Which is going to be closer to, let's say, to a usable level, to something that people can actually put their data on. right now, because this one is a little bit of the part like a kit car. This is not at this point. This is not a full solution. This is just part of something designed to to play with existing software-defined storage stacks, and they can't use it.
Yeah, I think the part people haven't figured out yet about NVMe over Fabrics is that it takes not just the SCSI cruft out of the operating system, but a lot of that SCSI cruft is that in the lab, I'm constantly playing which queue did I exhaust. When the queue depth gets to 128 and performance falls off, is that the HBA? Is it the virtual HBA? Is it the virtual SCSI layer? Because all of this stuff, while LSI has taken their stuff and gone, well, we used to give you 8 entries in the queue, and now you're going to have 256.
Amazing.
That it's not nearly enough, and because the whole underlying SCSI thing was designed around devices that can only do one thing at a time. A hard drive can only read or write from one of its heads at a time.
And it was like 17 inches away, ideally, right? I mean.
Yeah, and so it's the parallelism that one NVMe SSD that's got 8 flash packages that each have 8 flash chips in it can do 64 things at a time.
Yep.
And if I don't have 64 queue entries...
But I think you're right. You have to focus on the things that you can do with this that you can't do with the other technology. The multi-point to multi-point. There's a couple key things that really kind of stand out as, wow, now that's an option? I didn't know I could do that, And that's what's going to be important.
And then there's the whole composability thing. Then there's just that we don't have shelves of drives connected via SAS to a pair of controllers, but we have shelves of SSD connected to 100 gig Ethernet so that they can be sliced and diced among 20 pairs of controllers dynamically.
Right.
So
Now,
even if it's not faster, it's still better.
That brings up the question, is there any distance limitations and things of that nature for 100 gig?
100 meter, 25 meters on direct attach cables, hundreds of meters once you go fiber.
Hundreds upon hundreds.
And so data center scale.
Yeah.
And that's what makes TCP, NVMe over TCP interesting. It's like, yeah, it's going to add 20 or 30 microseconds of latency.
But
it means that I have resources across even a Google-sized data center that can all be usable anywhere. And sometimes you go, well, 20 microseconds, I'll pay 20 microseconds for that. That's not all that much.
Yep. The comment you made about the upper layers not being able to take advantage because they've been writing to all these older things. In other tech, verticals, what we have sometimes seen is that when someone like you guys come in and really kind of drop the floor out at a lower level, every once in a while there's someone above it that notices and tries to take advantage. Is there anyone out there that you would be wanting to work with, or are you guys looking to develop the whole stack yourself?
We'll see how it goes. So this is a typical approach. So throw it at the wall and see will it stick it or not. So we have the first early adopter, which is ourselves. So it's not something like we build a technology and we have no idea what to do with it.
Right.
So we are using the same like happened with us with ISOR. So we built an ISOR on Windows, and nobody has except us as an initiator on Windows. That's why we keep our DMA traffic as a backbone of our own storage and hyperconvergent appliances. We don't really care. So people use ISOR on Windows like thousands of them without even knowing that's there. Yep. And the same is going to happen with the first implementation for our all NVMe flash appliances. So we'll play like guys already mentioned. We'll ditch ISOR and put NVMe as a fabrics, because if it's just NVMe as a storage, it makes sense to go with a lightweight protocol that is designed right to do the right thing.
And why stick SCSI in the middle?
Yeah, exactly correct. I mean, it's not that much of the overhead. It's exactly the amount of the queues. So somebody in the whole storage stack, somebody is going to act as a weak link, and he'll drop off. And this is what Microsoft is trying to do right now. Say they have exactly the same issue with persistent memory, which is NVDIMMs or whatever it's called this week. I don't know. The classic model of Microsoft of storage stack doesn't work really well. So they have to move the actual driver one level up, one level up, one level up to a point when I think it's a class driver right now. So the topest possible driver in the kernel. And I believe it's a completely wrong way to handle the high-performance memory. So it should be application in the user mode that knows what to do with the data. So we are moving away from block devices, file system, the same way like we're ditching queues and all these single operation per time devices. We're getting to a point when application, like if it's a backup application and it talks object storage and it doesn't care about, doesn't care about file system, block device. It's just if there is somebody who is able to map the S3 object to super fast NVMe flash, that's what it needs right now. And it means that we need to redesign at some point not only operating system but also an application. This is already on the way. So unfortunately, operating system guys, especially the big ones, they're getting very slow in adoption, and we'll see the faster adoption of high performance technologies. For example, from maybe from SQL Server, from Oracle. I mean, the teams that are working separately from from core teams. The same about data centers. So Azure clearly has fundamental issue with low performance of object storage. So either you are paying pennies for slow storage or paying real big amount of money for pinpointed NVMe. There should be something in the middle. It's not like people are getting either Ferrari or or Prius. There should be Camry, some like F-150 truck and so on. So they will appear. There's clear demand for that, and these guys will be driving the adoption. So data centers, the database guys, and somebody who wants to build their point-to-point connections between the data centers. And if they don't run the DMA fabrics, which is limited in distance, and using different transport, but at the same time it will be NVMe over something. So these guys will help with the adoption. And another thing about interesting about the architecture we had represented right now is we're hitting different, I would say, problem, all of us. So operating system, they're getting more and more complex. So the amount of the code that runs in kernel, it just increase. So something fails, and it takes the whole host down. At the good old times when guys like Sun Microsystems, Digital Equipment, they controlled the whole stack, and they tested their hardware against their software, and everything was easy. Right now we have a bunch of the guys who are releasing their not very well written drivers, and operating system vendors had just forced it to throw them into kernel because they need to support this new hardware. For GPU guys did a first leap with moving their code into moving megabytes of the source code and very big executables to user land. So ideally, we would like to have all the same, because CPU is the cheapest resource we have right now. So nobody has a problem with with getting 20 cores instead of 10 cores if he wants more stability for his operating system. So what we're trying to do right now, we're trying to virtualize drivers. At some point, we'll see more products coming from our company that going to be written this way. So definitely we'll be bringing a RAID to VMware vSphere that is built on the same approach. Because if we're cutting away the network fabric layer and we're just taking local NVMEs, we can erase the code or replicate them inside the virtual machine, and we can use the same stub driver, just mapping memory to the virtual machine and providing this pooled fast storage to operating system. And if something goes bad with it, no problem, it will be just virtual machine rebooting. It's not like we'll have a purple screen of death for something. And right now, the same could be implemented for all the drivers. So leaving as small amount in the kernel level as possible and having everything moved either to user land, doing polling, or just isolated into dedicated virtual machines. That's going to increase stability, and from our side, we think that's the only way to go. because we're already dealing with such a big complexity that doing an isolation and separating everything is the only way to go. That's it.
Yeah.
So, again, I'm going to kick you all back into action here. I guess the question is, as new storage technology comes and as truly transformative storage technology comes, how does that change the overall system architecture? So you just heard about, for example, moving all of this into user land. And we've heard that from other companies at Tech Field Day in the past as well. We've heard from companies that are trying to implement storage in user space so that they don't have to, go into kernel mode. We've heard here about, many cores, right? I mean, we've got a 32-core single CPU sitting in our office right now, and in our testing of it,
Sweet.
Oh, it's sweet. Let me tell you, it's amazing. But in our testing of it, the question arises: what do you do with all those cores? I mean,
you run a whole bunch of VMs.
And that's a real good point. I mean, so we've got Dell EMC making a 32-core single CPU server chassis now. So does that, things like this really transform, fundamentally transform storage architecture? The idea that you want to get things out of a core quickly and into another core quickly so that you can try to leverage all those cores. All these old protocols, all these old assumptions don't work anymore. I don't know. What does storage look like going forward? This is a big picture.
I think one interesting advantage this time is that I think in previous, when new transport technologies have come up, there have been array vendors and large vendors that have had the ability to slow things down and avoid things that they didn't see that was advantageous to them. And now we have a more open market, at least for this type of technology, where you have Intel and others getting into it, and there might be a less resistance to some real fundamental change.
It's shocking.
I think there might be still.
Oh, there is, but I'm just saying less. Right?
Yeah, but it's still going to take a lot of discussion and a lot of teaching people within certain parts of a company to get them to use these kind of storage.
Absolutely.
The shocking part to me isn't the obstruction, but how quickly the big boys have said NVMe over fabrics. We do that too.
Well, it becomes disruptive.
Well, it happens all the time.
Dell EMC and NetApp.
We want to show that.
IBM.
Dell EMC, NetApp, and IBM are all at we're ready to ship.
And Pure is shipping, yeah.
NVMe, well, Pure shipping on the back end.
Right.
Not, but they're ready to ship. Here's a PowerMax or an all-flash FAS that you can access via NVMe over fabrics and get that lower latency. Now, they're almost all NVMe over fiber channel.
Yeah.
But frankly, I think NVMe over fiber channel is what the customers of those products are going to buy anyway.
Yes.
Yeah.
We as engineers may go, well, why am I going to run fiber channel? I could run Ethernet. But the guy who is going to buy a PowerMax is likely to put it on fiber channel whether there was an Ethernet option or not.
That's the reality of what we have right now.
Well, and buffer credits are a good thing.
And at some point it has to be lossless. And there's just the storage team owns the fiber channel switches, and if we put in Ethernet switches, we're going to have political battles with the network guys over who runs the switch that's at storage. And I don't want to have that battle. I'm going to stick with fiber channel, is how a lot of storage guys are going to respond to that.
I think the traditional array structure is fairly resilient and has survived, 4 or 5 different generations of protocols.
Yeah, that's true. Remember our first.
But in all that time, to some extent, storage was very expensive, so you wanted to amortize it across multiple users.
Yeah. Right.
So storage is still somewhat expensive, but performance has dropped out from nowhere. I mean, these guys can do, roughly millions of IHOPs in a couple of devices. So the price of performance is coming down drastically.
Yeah, the price of performance has dropped to the point or in this next round, drops to the point where I think we stop even thinking about performance. That
for a while.
Till a new round of applications that won't work with latencies over 300 microseconds comes around. Because that always happens too. That when a new generation of hardware is faster, for a little while, you go, wow, this is really fast. The software guys have to catch up with this. And then the software guys come up with something that barely works on the current generation and needs the one after that.
Yes, of course.
To work
because
properly.
they are lazy and they don't optimize the code.
Yeah, well,
that's another.
I wouldn't go there, but okay.
But Ray is right about the storage array. I mean, it just reminds me. The first storage array that I saw, had big, thick, parallel cables on it, and then we moved on and on and on and on, and pretty soon, people are talking about the death of the storage array. Is NVMe over Fabrics the death of the storage array? Let's hear from somebody else in here. Is
okay,
this
I'll
the
shut
end
up now.
of the storage array? Or
No.
is this just the beginning of the new storage array?
We're still going to need it.
Go.
We're still going to need the storage arrays. We're going to need the capacity. We're going to have the legacy of these things that are around, that even enterprises are just not going to be able to wrap their heads around this or the composable architecture. They're still going to need their legacy comfort blanket of storage arrays.
Maybe now we can really talk about composable infrastructure. Up to now, you had a lot of discussion about composable infrastructure, but every time I saw the presentation from the vendors, I thought more about, okay, this is a box. You put things in a different way, but doesn't change anything.
Yeah.
Now you are starting to talk about data center level components that you can manage to make your specific stack for that application, and you can change it
because
almost online without disruption of service and so on.
I don't really care that I can assign the 24 disk drives in the disk bay in a blade chassis to any of the blades.
Right.
No,
That degree of, yes, that's composable.
Yeah.
But the degree of composability of a blade chassis is too small for me to care that it's composable.
It was a nice demo.
but if the unit of adding storage to the data center is a 2U JBOF with 24 SSDs in it that's Ethernet connected,
And I can just
have
just litter
a
them
rack
around
of
anywhere,
those in the middle of a row, and that's all the media for the row, and then a software-defined storage layer for the applications that need snapshots and RAID and those levels of protection.
And that 2-year 24 SSD is capable of 6 million IOPS and
you like this
48 gigabytes
discussion
per
on the
second
median
of
of IOPS,
bandwidth, and operates at 100 microsecond latency. Jesus.
and again, you don't even have the problem of the controllers anymore because you can implement everything on software. And now FPGAs or ASICs, not ASICs, but FPGAs are a good example. No? Some vendors are moving to that kind of compute to make things happen fast.
Yeah.
To keep up with the so it's just changing the way we think the compute part for data protection and stuff to keep up with the NVMe drives. But it's
50
But it
gigabytes
really
per
sounds
second.
like you are talking about the end of the storage array. I don't hear a storage array here. I mean, I hear a new
it's a
data
virtual
center.
storage array.
A virtual storage array.
It's it becomes virtual because
Software-defined storage.
Made of very hardware components because you need, it's again, you can't trust even if it's a 32 core CPU, you can trust a standard general purpose CPU to make such operations.
But it is still more Clarion than symmetric. I mean, like we are talking about like much smaller Lego pieces, right? You're not talking about the big frames that we had in the past. But it's going to take. I mean, look, even if the technology was baked ready today, did everything you wanted, made you toast and espresso, it would take what 7, 8 years
at least
for some people to even start looking at it, right? So it's this is stuff. I forget what someone quoted once, like this, 2% change a year is about what most data centers can tolerate. So, I don't know if it's that extreme, but this stuff takes time.
Yeah, I definitely see a place for NVMe over Fabric front end and back end arrays. PowerMax.
Yeah.
All flash has. That's going to be around at least 3 purchase cycles, so at least 12 years.
Yeah.
But the more cost-sensitive projects, the more innovative customers will start disaggregating that array from a product I buy from Dell or NetApp, where the controllers, the software, and the media are one SKU, to the media device is a SKU,
Right.
and I'm going to layer the software-defined storage on it. And there's a huge amount of orchestration stuff that I'm seeing in back rooms of places where, a vendor who has a scale-out shared nothing device now says, okay, I'm going to take that software and I'm going to add the orchestration for grabbing namespaces from a JBOF. And so I'm going to say, build a virtual array that's got 4 controllers. And when the latency on accesses to that array exceeds 2 milliseconds, spin up 2 more controllers. Or
Absolutely.
at the end of the month when I'm going to do the data load,
Yeah.
and it's a deduping system, so I'm going to need a lot of CPU, fire up 6 more controllers.
Schedule that ahead of time.
Schedule that ahead of time.
Well, I mean,
Plenty
you might
of
have to
compute
schedule it.
horsepower to do the dedupe in that task, and then revert that compute resource back to the. What it comes down to is consolidating the free pool.
Yeah.
We all know one big pool is more efficient and easier to manage than a bunch of fragmented pools. And if compute and media become pools, you could have, there's reasons why the storage controllers as VMs are less persistent.
Yep. But there's already precedent for what you're talking about. I mean, even you go to like e-commerce places. I mean, there's a number of places that run on X number of VMs normally, but if a sale triggers, if it's a Friday with a Monday holiday, they can spawn up to 400-500% more VMs than they normally run on just to handle those spikes, right? So there's good case for what you're talking about. But let me ask you guys, do you think that any array vendors pushback or lack of support for FCOE hurt FCOE?
FCOE?
No.
No, don't start with the FCOE.
No, I'm not talking about FCOE, but
What? I'm sorry, I don't know what you're talking about.
Specifically the array vendors, the way they handled it. So I'm kind of curious as to how much differently are they handling NVMe than they did that? I don't remember.
FCOE.
I don't think FCOE had a performance advantage significant enough to warrant the technology to be invested in. NVMe over Fabric has got order of magnitude more performance, maybe double that. There's
but it's a different. It's totally different. FCOE was just
we follow this
collapsing
or we're dead.
protocols on the same media. NVMe is a totally different protocol to access the media.
No, but I was wondering,
so we can compare the two.
From the discussion of how much do the array vendors have control or pressure as to how fast this new technology comes, how much influence do they have? I was just trying to contrast this to whatever the last one was.
But this takes away a lot of their control because this makes it easier for an enterprise to drive their purchase cycle or their needs of an application to something that's a really cheap option where I'm not buying an entire storage array shelf.
I agree with you. So then why are they jumping on it on hot and heavy?
I think they want to control it. I mean, that's
get there first. Okay.
They want to have the name recognition of like we're there. We can stay with the guys that are actually innovating all of this and doing
and influence.
If I was an enterprise storage vendor who was selling refrigerators full of storage to companies, I would be scared to death of this thing because suddenly we've got, well, let's just say metaphorically speaking, a bunch of guys in the Ukraine writing some software that lets you do amazing stuff with
Bring your own
something
mini fridge.
that you just brought in. I mean, as we said in the discussion earlier, I mean, I think Ray was the one that was saying it. Suddenly you've got a couple of servers, maybe super micro servers or whatever, maybe home built servers for all that matters, and you got some switches, you got some NVMe devices, you run some software on it, and suddenly you've got something that's way better than that main battle tank that you used to buy. They've got to get in front of this.
Yeah, Dell and NetApp don't want a startup to get in the data center with this.
And there's a lot of just like with Flash. Remember, the all-flash array washing, where people would just chuck the disk over one shoulder and stick an SSD in the other shoulder and say, "Yep, it's an all-flash array." We're getting NVMe washing here, right? So we're going to start seeing companies coming out with the same old thing they always made, except now with NVMe. I mean, it's one of those TV commercials, right? Now with more NVMe, and is that really NVMe storage? No, that's just some old array with a bunch of new stuff stuck in it somewhere way down deep.
No, but for a lot of people, that's the check the box.
Yeah.
They have the option.
But all those array guys came out with actual new storage that was focused on flash. So I mean, they'll get there. The question is, how long will it take? Can they fend off the startups, quote unquote, until they've gotten something that's comparable?
Do they need to, though? Do they need to fend them off, really? I mean, the startups can have their little piece of the pie. These guys can trundle along at their own speed, and eventually they get there anyway.
They're already an approved vendor. They're already in the purchase cycle. It's already I've got a plan to swap the next model.
But you're still talking fundamentally
about... This is disruptive from the bottom side of things. These guys are coming in ultra cheap with ultra high performance.
Right.
This is like a line item hides. But you can provide software-defined storage. And these guys are going to sell to smaller organizations or more innovative organizations. They're going to build a niche from that point and start entering the enterprise.
Yes.
It's just if all goes well and the major vendors don't address it.
Right, and the major vendors have.
But there's also a fundamental change from vertical to horizontal concepts and integrations and so forth. I mean, think about, it was a pretty short period of time when we were all running really, really big Sun systems, and then we were running a bunch of little tiny Linux systems, and it was good. We got a lot out of it, right? But if you talk to people 2 years before that and ask them, do you think this is going to happen? I mean, I don't know how many of you remember, but there was a time where if you mentioned running Linux in production, people laughed.
So,
right?
One thing I really like with NVMe, what I find it like a revolution and a transformative thing, is that it's really, we used to have, so CPU were always fast, memory was always fast, disk was terribly slow.
Mm-hmm.
It's now bringing everything more or less at the same speed levels, at the same latency levels, and we're no longer relying on some kind of spinning, rotating media. Everything is just memory, silicon. So we are everything at the silicon level, and for me the true transformation is when we're going to be able to let's say slice resources at the silicon level. So that's what you were saying before. Like go into a truly composable system or a fully disaggregated system where you just have an orchestrator system which is on top of that, and you just slice, cut, however you need it, and you're no longer dependent on anything. And you may have all of the functions that you need from a storage array in terms of resiliency, in terms of data protection, replication, compression, whatever you need. All of that should be built into the storage. There's no reason why you have to depend on a 2-controller unit or a 4-controller unit, which is a legacy design by now, in fact.
But
we have it because we're used to it, right? It's like you have cars using petrol. You're used to it, but why not go to electric or something else?
No, I totally agree. The only thing I was going to add is that I think it's probably a little dangerous to assume that we're going to end up in any kind of level of normalization for any length of time. You're going to, at some point, one of those components is going to see a significant performance increase, and you start the race all over again, right? So, so it's one of the challenges that of composability.
One of the other challenges that we always had is the fact that scale-out storage was not promising the same consistency in performance than scale-up storage.
Yeah.
Yeah,
So
agreed.
anyway, or it was the story at least. Okay. So now you have removed the performance problem.
That's
okay,
true.
at every level. So potentially any sort of scale-out storage, the distributed storage, will work. We are not there today, but actually it will be faster, it will be more resilient, it will be everything more than your old scale-up storage. The 2-controller storage or the 8-controller storage, but in a box, was just more predictable. And this is one of the reasons why the old storage manager was there. They said, this works. Okay, all your fancy scale-out stuff, it's nice. You have some advantages, but think only about rebalancing of a scale-out cluster. Oh no, I have a problem in performance, and it will happen on Friday. Okay, when I have to go home. Now with NVMe 2 million IOPS, you will never use 2 million IOPS from a single server. But you have 2 million IOPS. If you have to, to do some rebalancing, okay, it will take
so in
minutes.
graded mode, you're down to 1 million hours, which is plenty.
Okay. Then you have your not optimized application that will suffer anyway, but still 1 million IOPS from a single box.
The graded mode reduces your headroom. It doesn't put you into, oh my God, things stink.
Yeah, one of the things I really liked was listening, and you can turn up the IOPS based off of your CPU count. So yeah, you were talking about like a 36-core CPU host. Now you can spin up or dial back or dial up specific workloads when you're ready. I think that's probably one of the big dramatic differences.
So the present Titan supercomputer at Oak Ridge National Labs generates about 2.5 terabytes per second over 18,000 plus nodes. With this device, roughly 60 nodes, it's roughly the same 2.5 terabytes per second. Does this make any sense to you? I mean, it's a lot of storage. It's 1,250 Optane SSDs, but these guys got lots more SSDs and 18,000 nodes to do that.
Well, then you have the capacity.
Yeah,
so these are small devices.
I understand. This is phenomenal.
Yeah, it really is. It really is.
2 gigabytes per second per Optane SSD. It wasn't that long ago where a mainframe array could barely hit a gigabyte per second. This is 10 years.
Yeah. Well, I remember.
All right, maybe it's 20.
I remember I used to do storage seminars, and I used to try to, as a mental exercise, tell people, well, what if capacity was free? And then, of course, the secret was, surprise, capacity is already free. You're only really paying for performance.
Yeah.
Now, suddenly, we're saying, what if performance was free?
Yeah.
I mean, that really flips everything on its head.
One of the things, this conversation is something like we went through 6 years ago, maybe 5 years ago, when Flash was first introduced, and the same conversations of what we started to go through with the vendors, or when I started getting more into it in the storage side of things, was performance started to become something that we didn't figure, or we didn't want to talk around with the customer. We wanted to talk about the applications and what you're trying to do and how you're trying to do it. We were all amazed at the performance of what you're going to get from Flash. We're still going to see that side of things as we start to go through this again. Now that the technology is changing, it's going to be a consolidation. So we consolidated down from spinning disk into Flash, already consolidated down the storage, and now we're doing it with NVMe, where we'll be able to consolidate down again. So going from that 18,000 nodes to, 60 nodes, was it? Or something like that then. So going down again, consolidating down again, being able to provide that performance. It's a cycle of the new technology coming round again, and I think that is going to be the hardest thing to grasp for a customer.
And it is different because before that you were talking about immediate increase. This is an immediate increase with a different transport protocol, right? So I mean, it's a different. It allows for a greater shift of your design process.
But I don't want to underestimate the fact that you are producing, a throughput that is amazing, 2 gigabyte per device. You will still need capacity because you fill up your 100 gigabyte device Optane in 50 seconds.
Yeah.
All these things doesn't make sense. Okay, so you will need terabyte and terabyte. So you will come down again in the performance because you will need 30 terabyte, 50 terabyte SSDs, which are made of QLC and they are way slower than your Optane. So yes, so the design is, ideally speaking, very cool. The reality is a little bit different,
Yeah, but even with flash NVMe SSDs, we're talking about latencies in the 100 to 120 microsecond range.
And I will say that,
but how much
and
does an SSD cost today? It's not as cheap as a disk. Not meaning
but first of all, SSDs have reached the enterprises don't consider them expensive stage.
Oh yes, no.
And second of all, in the next 18 months, those prices are coming down 50%. Toshiba opened a new fab today.
Oh, that's right.
The capacity to make flash is increasing for lots of reasons, and those prices are about to plummet. So today,
and all the vendors with 3D NAND can do many more layers than they can do today. So in the next few years, they will be able to do.
Optane is only 2 layers.
So today, 4 terabyte NVMe SSD costs between 8 and 10 times what a same size spinning disk costs.
And the one thing I will add to what you said, though, is I agree with what you said, except for the one change now is that we do have some interesting application verticals. You look at machine learning, for example, and so forth, where you do need memory spaces where you're doing a lot of very high throughput work, but you don't necessarily need a lot of storage, right? Whereas before, I think that what you said was probably more true, more ubiquitously true. I think now we do have some kind of examples. You take a driverless car, right? I mean, the kind of latency you're going to want in those kind of situations. I mean, there's lots of specific little places now that exist where I think you could still benefit from this without needing the capacity, right? Not enough to maybe offset, but certainly more than we had, 10 years ago.
Well, this is awesome. Thank you very much for spending some time talking about NVMe and the transformation here. What comes next? What should we talk about next in the industry?
It's a good question. In the industry, you really want me to tell?
Yeah. We're all friends here, Anton.
Really?
Nobody's watching.
Okay, nobody's watching.
Almost.
It makes things easier. So next thing will be, so somebody mentioned over here the composable computing. So it turns out that at some point we're going to stop seeing computers at all. So everything will just, like at some point, some people were hosting their websites with the modem connection back home, so with using normal phone lines. Nobody's doing this right. I mean, nobody's doing this anymore. The same is going to happen that at some point we'll see that all the services, everything we do, is getting completely virtualized. So there will be somewhere one big data center, and when you'll be, instead of buying computer, instead of buying yourself a server, you'll just be renting some machine time, like it was back in 60s.
Mm-hmm.
So what you'll get, you'll have a cell phone and as a terminal, and or whatever device which is going to be a connector between you and a gateway between you and this your virtual server, and this is where everything is going. So all the on-premises stuff we're talking about, or all these, arrays and, what's going to be, is this NVMe Fabric going to be a protocol, or is it going to be a next big thing for whatever? Everything is going to disappear. So people will stop buying servers, people will stop buying, storage arrays, and will just, there will be some kind of the data center infrastructure somewhere, and even big Fortune 500s will move all of their workloads away from their private data centers somewhere else. So that's going to be future, and for everybody who's not thinking about the transition of their technology, like is it will be useful in a huge data center, in whatever else, and who's putting his bets on on what's faster storage, what's slower storage, like backup stuff, on-prem stuff. He'll have to find a new job for himself, which is a little bit scary, because it turns out that lots of people in this room are at the risk. So that's.
But I mean,
this is what's that?
Well, what you're talking about. I mean, in HPC, this is what we've been seeing for years, and just a little bit ahead of the curve, right? I mean, you have these giant clusters where no one has any idea what hardware is in there, no one has any idea the speeds and feeds of anything. All they care about is how long it takes a job to get done. It's all job focused. It's all process focused. And in those cases, what you typically see is you see a lot of people like us move up into the optimization side of things, right? How do we take advantage of that kind of hardware? So I think for most people it's an uplift, but I think that there's if you look at some of the HPC environments, you will get hints and clues as to. It's not to say that enterprise will evolve the same way. It rarely does, but it often gives you clues as to how it might look and how it might play out. And what you're saying is definitely come out to pass in a lot of HPC environments.
So, engineering is a job. Software engineering is a job, and parallel programming or parallel software engineering is actually a black art, which means that it's not very difficult to build. To set up a cluster and do a huge amount of nodes, like thousand hundreds, easy. It's not very difficult to put to put multiple flash controllers on the same PCIe card and make it working in parallel. It's only a question who is going to be able to use it with a proper algorithm. Yes. Like is a database that is running it. If it just assume that can be one operation at a time, it will be all about latency, but not about parallelism. So that actually brings us back into re-engineering much of the software and getting rid of the middleman. So most of the operating system services have to die, because I do not believe that the parallelization of something can be generalized or can be automated. It's actually the exact final user has to rethink what he's doing, and to think about the computer not as just one CPU, but set of CPUs. Let me give you an example. We're in 2018 right now, and there is a Windows operating system, and they have a nice SCSI initiator that was written like 15 years ago. And every time you spawn a new session, new connection, instead of putting this connection on a new CPU core just to make all of them usable, it randomly puts them on the different ones. So it can be a new connection being assigned to already hot 100% used CPU, and there's like 15 right now that doing nothing, and still it works. So this is what we have in production right now, running on like thousands and millions probably of servers. So, and this is not fixed. This is the example from storage industry from today. So if people won't think about this brave new world coming, we can engineer whatever you want. But if the final that like there's last mile problem, there is also human factor, which is if people don't know how to use the technology, you can do brilliant things, and they will be just doing nothing will be pretty much a waste.
Well, but that's part of the story with this, right? Is as this becomes cheaper and as it becomes more available and more accessible to everyone, the people that can think that, we're changing a lot of what we're doing because the things that we do inside of our HPC environment, where we can compose and say, this thing runs better on this hardware, this runs better on this hardware, it makes everything around. We're starting to transition that into what we do with the enterprise infrastructure. And getting this out in front of more people, making it more accessible to have this performance out there, people figure out how to drive it better.
This is exactly correct, but it gets us from the technology to education.
Right.
So this, which is not my specialty, and unfortunately, I think that most people are thinking their biggest target in the life, to get out of the work at 5 p.m. and make sure that their boss won't call them and get them back. So that's their highest priority when it's getting related to work. And this is not something we're going to change it. And I don't think it should be changed.
Yeah.
So let's just provide people with a reliable, fast technology, and let's not speed them up. So I got a big passion in doing what I'm doing, and I got some other people paying for what I do, which is absolutely lovely thing to have. And I just enjoy what I do.